Imagine forces out there, forces so vast, so powerful, they can actually ripple the very fabric of reality itself.
Mm-hmm.
We're talking about gravitational waves today, and we're going to take a deep dive into these, well, frankly, incredible cosmic phenomena.
Absolutely.
So the big questions are, what are these waves, really? And why are they proving to be so profoundly important for how we understand the universe? Okay, let's try and unpack this a bit. For centuries, we had Newtonian physics. Gravity was just this instantaneous force.
Right. Action at a distance.
Exactly. Apples fall, Earth pulls them, seems simple enough. But then Albert Einstein came along and just completely turned that on its head with general relativity.
He really did.
Einstein showed us gravity isn't quite a force like we thought. It's more a result of space-time itself curving.
Precisely. Think of space-time as this huge flexible sheet, maybe like a trampoline.
Okay.
And massive things like stars, planets. They're like bowling balls sitting on it, creating these dips, these curves.
And when those bowling balls move...
That's the key. The dips and curves change, and those changes, those disturbances, travel outwards, like ripples on a pond.
Ah, okay, so those are the gravitational waves.
That's exactly what they are. In essence, they're oscillations, you could say, wobbles of that gravitational field, of space-time itself.
Wobbles in space-time, I like that.
Yeah, they are literally ripples in space-time traveling out at the speed of light.
Wow.
And they're generated whenever massive objects move relative to each other in certain ways. And crucially, they carry energy away as gravitational radiation.
Which sounds a lot like electromagnetic radiation, like light-carrying energy.
It's a very similar concept, yes. It's
Yeah.
fundamental to gravity. But something Newtonian physics just, well, it didn't have room for it.
And that's really our mission for this deep dive, isn't it? We want to explore these fascinating ripples, understand the incredible decades-long struggle scientists faced just trying to find them.
It was a struggle.
Figure out what kind of mind-boggling cosmic events create them, how we finally managed to detect them, and maybe most importantly, what new secrets they're already starting to unlock about the universe.
Yeah.
So consider this your shortcut to getting up to speed on something that is, it's genuinely groundbreaking stuff. Now, here's where it gets really interesting, I think. The biggest hurdle, the reason they were so hard to find for so long, is just their incredibly tiny scale.
Oh, absolutely minuscule.
When a wave passes by, it sort of stretches and squeezes the distance between objects. But how tiny are we talking here? Can you give us a sense of that effect?
It's almost hard to picture. Let's take that very first direct detection.
Yeah.
GW 150914.
Okay, the big one.
That wave had traveled for over 1 billion light years, right?
Right.
By the time it reached Earth, it changed the length of one of LEGO's arms, and those arms are 4 kilometers long.
Uh-huh.
Changed the length by just 1/1000th of the width of a single proton.
Wait, 1,000th of a proton width over 4 kilometers?
Exactly. I mean, to put that in perspective,
Yeah.
proportionally, it's like changing the distance to the nearest star, Proxima Centauri,
Yeah.
by the width of one human hair.
Wow. Okay. That's why it took so long.
That's the challenge.
Yeah.
The strain, which is what we call that fractional change in length, is typically around 10 to the minus 21 when these waves get to us. Just incredibly faint.
Makes perfect sense now. And what's fascinating, too, is the history, right? This wasn't just an idea Einstein plucked out of thin air. There were hints beforehand.
That's right. People were thinking along similar lines, drawing analogies with electromagnetism. Oliver Heaviside back in 1893, Henri Poincaré around 1905. They had some early theoretical ideas.
Interesting.
But yeah, it was really Einstein in 1916, working through general relativity, who formally showed that these waves should exist as ripples in space-time.
But even he wasn't totally convinced at first.
Not entirely, no. It's quite a story. He actually doubted their physical reality for a while. In 1936, he even submitted a paper arguing they couldn't exist.
Really?
Yep. But then, after the peer reviewer pointed out an error, he rewrote it, thankfully, concluding the opposite.
Huh. Okay, peer review saves the day.
It certainly did there. It was such a confusing time conceptually that Arthur Eddington even joked about certain wave solutions just propagating at the speed of thought because they seemed like mathematical artifacts.
So it sounds like a real conceptual muddle for a while there. Was there a moment or an argument that really settled whether these waves actually carried energy, whether they were physically real?
There was. Richard Feynman came up with this brilliant thought experiment in 1957. It's often called the sticky bead argument.
Okay, sticky beads.
Yeah, imagine a rod with some beads threaded onto it, able to slide, but with a bit of friction, sticky beads. As a gravitational wave passes, it would try to move the beads along the rod. Because of the friction, this movement would generate a tiny amount of heat.
Ah, so heat means energy transfer.
Exactly. If you can generate heat, the wave must be carrying energy and doing physical work. It was a simple, elegant way to show these waves weren't just some mathematical trick. They were a real physical phenomenon.
And that realization must have really set the stage for the immense challenge of actually trying to build something to detect them.
It did. And people started trying. Joseph Weber in the 1960s was a real pioneer. He built these huge metal cylinders, Weber bars, designed to resonate, to sort of ring when a gravitational wave passed through.
Did they work?
Well, he claimed detections in 1969, quite regularly, actually, but
Oh.
unfortunately, those claims couldn't be replicated. They were later shown to be spurious.
Ah, okay.
But his efforts, even though ultimately unsuccessful in detecting waves, were crucial. They really highlighted just how incredibly difficult this was going to be and spurred on the ingenuity needed for the next generation of detectors.
So decades passed between those early attempts and the first actual direct detection. But there was a really important piece of indirect evidence that came along in the meantime, wasn't there?
Oh, absolutely vital. The Hulse-Taylor binary pulsar.
Right. Discovered in 1974, and it eventually won the Nobel Prize in 93.
That's the one. Russell Hulse and Joseph Taylor found this pair of neutron stars orbiting each other. And by timing the pulses coming from the pulsar very, very precisely over years,
They noticed something changing.
they noticed the orbital period was getting shorter. They were spiraling inwards, closer and closer together, by just the tiniest amount each year.
And this connects to gravitational waves, how?
Well, if you connect this to the bigger picture, general relativity predicts that such a system must lose energy by radiating gravitational waves.
Okay.
And the rate at which Hulse and Taylor saw the orbit decaying, it matched Einstein's predictions for energy loss via gravitational waves perfectly.
Wow. So even though they couldn't see the waves.
Exactly. They saw the effect the waves must be having. It was incredibly strong proof that gravitational waves were real and behaved just as Einstein predicted. This gave huge motivation to keep building the incredibly sensitive detectors needed for a direct detection. It showed they had to be out there.
That's amazing. And just to give people a sense of how weak this effect usually is, think about our own Earth-Sun system. It's losing energy through gravitational waves too, right?
It is, yes, but vanishingly slowly.
Yeah, something like only 200 watts, which sounds like, well, not much for a whole solar system.
It's tiny. At that rate, it would take, what is it, something like 3 times 10 to the 13 times the current age of the universe for the Earth to actually spiral into the sun just from radiating gravitational waves.
Okay, so negligible for us.
Yeah.
But for those neutron stars whipping around each other.
Much, much faster.
Yeah.
Much more significant energy loss. It really put the Hulse-Taylor result into perspective.
Okay, so that brings us to the big moment, the breakthrough. September 2015, the LIGO detectors in the U.S., they finally catch one.
That's right. Livingston, Louisiana, and Hanford, Washington. Both detectors registered a signal almost simultaneously.
So what exactly did they hear or detect that day? What was GW15091 FAIR?
It was the signal from 2 black holes merging. And these weren't small black holes. One was about 29 times the mass of our sun, the other about 36 times.
Wow, those are hefty.
Very. And they were about 1.3 billion light years away. In the final fraction of a second before they merged into one larger black hole,
Yeah.
the amount of power they radiated as gravitational waves was just staggering. More than 50 times the power output of all the stars in the entire observable universe combined.
50 times. All the stars. That's insane power.
It is.
Yeah.
The energy equivalent of about 3 entire solar masses was converted directly into gravitational waves in that tiny moment.
Incredible.
And what's profoundly interesting here, beyond just confirming Einstein again, was the mass of those black holes. They were heavier than astronomers had generally thought possible for black holes formed from stars in binary systems.
So it immediately made us rethink things.
Exactly. It forced us to reconsider how these massive stellar black holes form and how often they merge. And because the signal arrived to the 2 detectors with a tiny time difference, just 7 milliseconds,
Ah, that let them pinpoint the direction.
it allowed them to roughly localize the source to a large patch of the southern celestial hemisphere. A monumental detection, really. And deservedly led to the 2017 Nobel Prize for Rainer Weiss, Kip Thorne, and Barry Barish, the key figures behind LIGO.
Just incredible. So this first direct detection, it wasn't just a confirmation, it really changed the game, didn't it? What's the biggest shift that gravitational wave astronomy has brought?
I'd say it's opened an entirely new window onto the universe, a new sense almost.
How so?
Its unique advantage is profound. Unlike light, radio waves, X-rays, all forms of electromagnetic radiation, gravitational waves basically aren't affected by stuff in between.
They just pass right through dust and gas.
Pretty much.
Uh,
They travel unimpeded across the cosmos, which means they can carry information about events and objects that are completely hidden from our telescopes. Things we've never directly observed before.
like what kind of things?
Well, black hole mergers involving uncharged black holes, for instance. They don't emit light, or maybe even signals from the very, very early universe.
Before light could even travel freely.
Exactly. A period when the universe was opaque to electromagnetic radiation. Gravitational waves could give us a direct probe into that era. We can now listen to parts of the universe we could never see.
Wow. Okay. And beyond that first huge detection, there have been other major milestones pretty quickly, right? Like the first neutron star merger?
Yes, that was another landmark moment, August 2017, GW170817.
What was so special about that one?
What made it incredibly significant was that it wasn't just detected in gravitational waves. It had an electromagnetic counterpart.
Ah, so we saw it with telescopes too.
We did. First, a short gamma-ray burst arrived just seconds after the gravitational wave signal. Then telescopes quickly found a new point of light, a kilonova, in a galaxy called NGC 4993.
So we saw the same event in two completely different ways.
Exactly. Gravitational waves and light. It was the birth of true multi-messenger astronomy. And having the Virgo detector in Italy online alongside LIGO by then was crucial.
Why was Virgo important?
Adding a third detector dramatically improved the ability to pinpoint the source on the sky. It narrowed down the location by about a factor of 10 compared to what LIGO alone could do. That's what allowed telescopes to find the counterpart so quickly.
That makes sense. The more ears listening, the better you can locate the sound.
Precisely.
And the discoveries just keep rolling in, don't they? I remember hearing about LIGO and Virgo finding the first neutron star black hole binaries in 2021.
That's right. Systems we'd theorized about but had never actually observed before by any conventional means. So yeah, the field is moving incredibly fast.
Which really begs the question, what other kinds of cosmic events are generating these powerful waves? Broadly speaking, what does it take to make space-time ripple like this?
Well, in general, you need large, coherent motions of really immense masses, especially in situations where gravity is extremely strong, where good old Newtonian gravity doesn't quite cut it anymore.
Okay.
But there's a crucial point. Not just any motion will do. Purely spherically symmetric systems don't radiate gravitational waves, meaning like a perfectly spherical star just collapsing inwards equally from all sides. No waves. Or an isolated non-spinning object just moving at a constant speed. No waves either.
So you need asymmetry, something uneven.
Exactly. You need a change in the mass distribution that isn't perfectly symmetrical. Think less like a pulsating ball and more like a spinning dumbbell, or two objects orbiting each other. Physicists talk about a changing quadrupole moment.
Okay, spinning dumbbell, got it. So given that need for asymmetry and huge masses, what are the prime suspects? The cosmic generator.
Top of the list are binary systems. Two objects orbiting each other.
Like the Hulse-Taylor pulsar we talked about?
Exactly. Or pairs of white dwarfs, neutron stars, or black holes. Now remember, the Earth and Sun radiate waves, but it's minuscule.
Right, negligible.
But get two compact objects like neutron stars or black holes orbiting really close and fast, they become powerful sources. Neutron star binaries can spiral in and merge in maybe just 36 hours once they get close enough. Then specifically, black hole binaries merging, like GW150918. The strongest burst of waves comes right at the very end, during the merger itself.
Makes sense, maximum violence then.
Then there are supernovae, star explosions. Unless the explosion is perfectly symmetrical, which is unlikely, the asymmetrical movement of huge amounts of mass will generate gravitational waves.
Okay.
And maybe surprisingly, even a single spinning neutron star can emit waves, but only if it's not perfectly spherical. If it has slight deformities like lumps or mountains, even ones maybe only 10 centimeters high, that asymmetry as it spins will radiate gravitational waves, though likely very weak ones.
10-centimeter mountains on a neutron star. That's wild. Such a range of sources.
It is.
This then brings up a really big question, especially thinking about the very beginning of everything. What about primordial gravitational waves? Could waves have been generated right after the Big Bang?
Ah, yes.
Yeah.
That's a huge area of research and hope in cosmology. The idea is that during cosmic inflation, this hypothesized period of incredibly rapid expansion just fractions of a second after the Big Bang. Quantum fluctuations could have been stretched to cosmic scales, generating a background of gravitational waves that would still be permeating the universe today.
And how would we detect those?
The main hope is to look for their imprint on the cosmic microwave background radiation, the CMB, the afterglow of the Big Bang.
Okay.
Specifically, these primordial waves are predicted to leave a faint, characteristic swirling pattern in the polarization of the CMB light, something called B-mode polarization.
Has anyone seen that?
Well, there was huge excitement back in 2014. The BIC-EP2 collaboration announced they had detected this B-mode signal.
Wow. So case closed.
Not quite. Unfortunately, further analysis, including data from the Planck satellite, showed that the signal they saw could be entirely explained by dust within our own Milky Way galaxy.
Oh, so it was retracted.
Yes, the claim was retracted in 2015. It was a tough lesson, showing just how incredibly careful you have to be and how faint these potential signals are. But the search definitely continues with more sensitive experiments. Finding primordial gravitational waves would be revolutionary for understanding the birth of the universe.
Absolutely. Okay, so we know where they might come from. How do we actually listen for these cosmic whispers now, especially given how tiny that effect is, the whole width of a hair to the nearest star thing?
Right. The workhorses, the most sensitive detectors we have on the ground right now, are these incredible machines called laser interferometers. LIGO is the prime example.
How do they work, in simple terms?
Okay, the basic idea is you have two long arms, usually several kilometers long, set up at a right angle, like an L shape.
Like Lego's 4-kilometer arms.
Exactly. You shoot a laser beam, split it, send it down both arms, bounce it off mirrors at the ends, and bring it back together.
Okay.
Normally, the light waves from both arms should recombine in a specific way. But if a gravitational wave passes through...
it stretches one arm and squeezes the other.
Precisely. Just by that minuscule amount we talked about. This tiny change in arm length means the light travel times are slightly different, and when the beams recombine, the pattern changes. That's the signal we look for.
That sounds unbelievably sensitive.
It is. LIGO can detect changes in distance as small as 10 to the minus 18 meters. That's a tiny fraction of a proton's width. And ongoing upgrades are making them even more sensitive, increasing the volume of space they can listen to by maybe a factor of 1,000.
And it's not just LIGO, right? There's a network now.
Yes, a global network is crucial. We have Virgo in Italy, Kirash in Japan is coming online, and there are plans for even more sensitive future detectors like the Einstein telescope in Europe and Cosmic Explorer in the US. Having multiple detectors helps pinpoint sources and confirm signals.
It's still hard to grasp that level of precision. What are the main things fighting against you? What makes it so hard to get a clear signal?
Oh, the noise is the killer. Remember that strain is maybe 1021? That signal is incredibly faint, easily buried in noise.
What kind of noise?
There are several main types. There's shot noise, which is basically quantum randomness in the laser light itself, photons arriving slightly randomly.
Okay.
There's thermal noise, just random jiggling of atoms in the mirrors and their suspensions due to heat. Brownian motion, essentially.
Right, things vibrating because they're warm.
Exactly. And then there's seismic noise vibrations from the Earth itself. Earthquakes far away, trucks driving down the road nearby, waves crashing on the coast. All of it shakes the ground and the detectors. Isolating the mirrors from all that is a massive engineering challenge.
It really sounds like trying to hear a pin drop during an earthquake next to a rock concert.
That's not a bad analogy, actually.
It's such a huge data analysis problem, too. I understand there's even a project where people donate their home computer time.
That's right. Einstein at Home. It's a distributed computing project. Volunteers run software that analyzes data from LIGO and the GEO 600 detector, specifically looking for the very faint continuous signals we expect from those slightly deformed spinning neutron stars we mentioned earlier.
Using the power of the crowd to sift through the noise? Clever.
It taps into massive computational power that would be hard to get otherwise.
So ground-based detectors are amazing, but face these noise challenges. Are there plans to go to space?
Yes, absolutely. That's the idea behind LISA, the Laser Interferometer Space Antenna. It's a major project led by the European Space Agency with NASA involvement.
How would LISA work? How is it different?
LISA will be completely different in scale. Instead of kilometer-long arms on Earth, it will consist of 3 spacecraft orbiting the sun, forming a giant equilateral triangle.
How giant?
The arms, the distance between the spacecraft will be 2.5 million kilometers long.
Whoa, okay, that's big.
Yeah, and being in space gives it huge advantages. It's away from Earth's seismic noise, and you get a much, much better vacuum than we can achieve on Earth.
So it can hear different things.
Exactly. Its huge size and quiet environment will make it sensitive to much lower frequency gravitational waves than ground-based detectors can pick up.
Hmm.
Things like mergers of supermassive black holes at the centers of galaxies, or binary systems of white dwarfs in our own galaxy.
Very cool. So ground-based for high frequencies, space-based for low frequencies. But I understand there's yet another way people are trying to detect these waves using pulsars.
That's right, a completely different technique called pulsar timing arrays, or PTAs.
Okay, explain PTAs. They use pulsars as clocks.
Precisely. They focus on millisecond pulsars.
Hmm.
These are incredibly dense, rapidly spinning neutron stars rotating hundreds of times per second. And they emit beams of radio waves like lighthouses.
Uh-huh.
From our perspective on Earth, as these beams sweep past, we see incredibly regular pulses of radio waves. They're fantastically stable clocks. Some are more precise than the best atomic clocks we have on Earth.
Cosmic clocks. Okay, so how do gravitational waves fit in?
Well, if we connect this to the bigger picture, imagine a very long wavelength gravitational wave, maybe taking years or decades to pass through our part of the galaxy.
Okay, a really slow ripple.
As that wave passes between us and one of these distant pulsars, it slightly stretches and squeezes the space-time along the path. This changes the travel time of the radio pulses very slightly.
So the ticks from the pulsar clock arrive a tiny bit early or late.
Exactly. PTAs monitor dozens of these millisecond pulsars scattered across the sky, looking for these tiny deviations in the pulse arrival times.
But how do they know it's a gravitational wave causing it and not something else?
That's the clever part. A gravitational wave passing through should affect the timing of all the pulsars, but in a very specific, correlated way, depending on their position on the sky relative to each other.
A pattern.
Yes, a very distinctive quadrupolar pattern. Pairs of pulsars in certain directions should show correlated timing shifts, while pairs in other directions should show anti-correlated shifts. It's called the Hellingsdowns curve. Finding that specific pattern is the smoking gun for a gravitational wave background. And also found it. This is the really exciting news from just recently, June 2023. Several PTA collaborations around the world, including Nanogrev in North America, released their analysis of 15 years or more of data.
Odd.
They found the first strong evidence for this distinctive Hellingsdowns curve correlation. It's the first compelling evidence for a stochastic gravitational wave background.
Stochastic meaning, like a background hum.
Exactly. Not a single big event like a black hole merger, but a persistent, universe-filling hum made up of overlapping waves from countless sources.
Wow. What's making the hum?
The most likely source is the combined chorus of hundreds of thousands, maybe millions, of supermassive black hole binaries merging all across the universe throughout cosmic history.
So we're hearing the biggest black holes in the cosmos pairing up and dancing towards merger, averaged out over billions of years.
That's the interpretation. It's not just noise. It's like an acoustic map of galaxy evolution and these giant black hole interactions over cosmic time. A totally new way to study how galaxies and their central monsters grow.
That is absolutely mind-bending, hearing the universe hum with merging giants. Okay, shifting gears a bit. Could humans ever, make gravitational waves here on Earth? In a lab? I mean, everything we've talked about involves stars and black holes.
That's a fascinating, very speculative question. Theoretically, maybe. People have discussed concepts for microscopic sources. There's even this idea of a gas or gravity amplification by stimulated emission of radiation.
Like a laser, but for gravity.
Kind of. The proposal involved using things like Cooper pairs and superconductors. But we're talking way out on the frontiers of theoretical physics here. Generating detectable waves in a lab would require manipulating mass energy on scales far beyond anything we can currently conceive of, let alone achieve.
So probably not anytime soon.
Probably not. It pushes right up against the limits of our understanding, especially where gravity meets the quantum world.
Which leads perfectly to that ultimate frontier, doesn't it? Quantum gravity, and this idea of the graviton. What exactly is a graviton supposed to be?
Well, in our current understanding of particle physics, the fundamental forces, electromagnetism, the weak and strong nuclear forces, are all mediated by force-carrying particles, like the photon carries the electromagnetic force.
Right.
Quantum gravity theories predict that gravity should also have a force carrier, a hypothetical particle called the graviton.
What would it be like?
It's theorized to be massless, like the photon, but to have a property called spin 2, whereas the photon has spin 1. But the key word is hypothetical.
It hasn't been proven to exist.
Not even close. We don't yet have a complete successful theory of quantum gravity that fully describes the graviton and how it would work. It's one of the biggest unsolved problems in fundamental physics, unifying gravity, Einstein's world, with quantum mechanics, the world of particles.
And that's where it gets really tantalizing, right? Because if we did somehow discover a massless spin-2 particle,
That would almost certainly be the graviton.
and what would that mean?
Oh, it would be profound, absolutely revolutionary. It would be the first direct experimental evidence confirming that gravity can be quantized, finally uniting quantum theory with general relativity. It would reshape our understanding of reality at its deepest level, one of the biggest holy grails in physics.
Wow.
Yeah.
Okay. What an incredible journey we've taken today, seriously. From Einstein puzzling over these ripples in space-time,
His own doubts included.
right, to the decades of searching, the indirect proof from pulsars, and then finally LIGO hearing those black holes collide.
And now the PTA's hearing the cosmic hum.
It's just opened up this completely new way of observing the universe, hasn't it?
It really has. And its power, particularly for looking back towards the beginning, is immense.
Because the waves just travel straight through everything.
Exactly. They experience very little absorption or scattering, even over billions of light years. Unlike light or radio waves, which get blocked or altered by gas and dust.
So they can carry information from eras we could never see before.
Potentially, yes. Phases of the universe that were completely opaque to light might be transparent to gravitational waves. They could let us probe closer to the Big Bang than ever before.
It really makes you wonder, doesn't it? What other profound secrets are these cosmic ripples carrying? Secrets about the most violent events, maybe secrets about the universe's very beginning, just waiting for us to get better at listening.
There's so much potential still untapped.
Absolutely. Well, definitely keep those curiosity engines running.